What if I told you that every time you walk across a room, you're achieving something that's logically impossible? That the simple act of moving from one place to another, something we do without a second thought, might actually just be an illusion. This isn't some futuristic riddle. It's a puzzle from thousands of years ago that still challenges the very fabric of reality as we know it.
I mean, really think about it. To get anywhere, you first have to go half the distance, right? Okay, simple enough. But then you have to go half of the remaining distance, and then half of that tiny piece that's left over, and so on, forever. You're left with an infinite number of halves to cross. So how do you ever actually get there?
Now, this isn't my idea. This is a 2,500-year-old thought experiment from an ancient Greek philosopher named Zeno of Elea. And let me tell you, it has stumped some of the greatest minds in history. And it all kicks off with what sounds like a really simple race.
So on one side, you've got Achilles, the fastest, strongest warrior in all of Greece. A literal blur of bronze and muscle. And on the other side, a humble tortoise. Now, to make things fair, Achilles gives the little guy a head start. Common sense just screams that Achilles is going to blow past that tortoise in a heartbeat. But Zeno's ice-cold logic says something completely different.
Here's the logical trap. For Achilles to catch the tortoise, he first has to get to the spot where the tortoise started. Makes sense. But in the time it takes him to run that distance, the tortoise is already inched forward to a new spot. So now, Achilles has to run to that new spot. But you guessed it, by the time he gets there, the tortoise has moved again. He's always arriving where the tortoise used to be, trapped in this never-ending loop of just catching up.
And this is the absolute core of the paradox. Zeno says that because the distance can be divided up an infinite number of times, Achilles has to complete an infinite number of tasks. And, well, completing an infinite number of tasks should logically take an infinite amount of time. So how can he ever catch up?
For over 2,000 years, this paradox was a massive philosophical headache. I mean, we all know from just living our lives that motion is real. You can walk across a room. The logic feels so wrong, but it's incredibly hard to argue against. That is, until mathematics gave us a completely new way to look at the whole idea of infinity.
The key was this mind-bending idea called a convergent series. And what it says is that yes, you can have an infinite list of numbers, a series of steps that goes on forever, but they can still add up to one single finite total. So think about it like this. An infinite number of steps doesn't always have to mean an infinite distance or an infinite amount of time.
Let's put some real numbers on this. Imagine the tortoise starts 10 meters ahead. So to cover that first gap, Achilles runs 10 meters. Okay, in that time, let's say the tortoise moves forward 1 meter. Now Achilles has to cover that 1 meter. But while he's doing that, the tortoise moves another 0.1 meters. You see the pattern, right? The distances Achilles has to cover get smaller and smaller and smaller, and they do it really fast.
And here is the beautiful power of that convergent series. When you add up all those infinite shrinking distances, 10 plus 1 plus 0.1 plus 0.01, and on and on and on, they don't go to infinity. They all add up, they converge to a very specific, very finite number, about 11.1 meters. And that is the exact spot on the track where Achilles finally catches and then overtakes the tortoise.
So math saves the day. The race is won. Achilles wins. But solving the numbers problem doesn't quite get rid of the deeper philosophical questions Zeno is poking at. Because the math only works if you can keep dividing reality up into smaller and smaller pieces forever. But can you?
You see, Zeno wasn't just talking about a race. He had other paradoxes too, like one about a flying arrow. He said, look, if you freeze time at any single instant, that arrow isn't moving, it's just there. So if it's not moving at any one instant, how does it ever move at all? These puzzles force us to ask a really fundamental question. Can you keep cutting space and time in half forever and ever?
The journey to figure this out is really the story of science itself. After Zeno posed the question way back in ancient Greece, it wasn't until the 18th century that calculus gave us the mathematical tools to even handle it. But the truly shocking answer, the one that changes everything, didn't come until the 20th century, from the incredibly strange world of quantum physics. What quantum mechanics suggests is that there is a fundamental limit to how small you can get, a shortest possible distance. It's called the Planck Length, and this isn't just about our technology not being good enough. It seems to be a hard rule of the universe. Reality, at its most basic level, might not be smooth and continuous. It might be grainy or pixelated like a digital image.
And just how small is one of these pixels of reality?
Well, it's a number so ridiculously tiny it's almost impossible to imagine. To give you some perspective, if you were to scale up a single atom to be the size of the entire known universe, the Planck length would be about the height of a single tree. It's that small.
So this brings us to the modern answer to Zeno. If space can't be divided up forever, then Zeno's main argument is physically wrong. Achilles doesn't have an infinite number of divisions to cross. He just has a ridiculously huge but still finite number of Planck lengths to travel. And from this point of view, the paradox just evaporates. Its core assumption about a smooth, endless reality turns out to be incorrect.
So we have our answer. Reality has a resolution limit, a final pixel. Case closed, right? Well, what happens if you try to look inside one of those pixels? What's going on at the absolute boundary of reality? This is where solving one paradox just uncovers a much bigger, much stranger.
You see, the Planck length isn't a simple finish line. It's a crisis point for physics. It's the scale where our two best descriptions of the universe, that's Einstein's theory of gravity and space-time, general relativity, and the theory of tiny things, quantum mechanics, they just stop working together. They start giving you answers that are complete nonsense.
Here's just how bizarre it gets. If you try to pin down a single particle into a space as small as the Planck length, a law called the uncertainty principle kicks in. It says the particle's energy would spike to become almost infinite. And according to Einstein, that much energy crammed into such a tiny space would warp space-time so badly that it would instantly collapse into a miniature black hole.
It's like a set of those Russian nesting dolls. You open one up and there's another one inside. Zeno's paradox about motion leads us to a math solution. That solution leads us to a physics question, which is answered by the Planck length. And the Planck length reveals this fundamental breakdown in all of our physics, creating a brand new paradox. Every time we solve one of these puzzles, we find a deeper, more profound one hiding inside.
So we've wrestled with the idea of dividing up space, but what happens when you take this exact same infinite logic and apply it to time? This brings us to a final thought experiment, kind of a modern cousin to Zeno's paradox, called Thomson's lamp. All right, picture this. You have a lamp, and it starts out switched off. After 30 seconds, you turn it on. Then you wait 15 seconds, half the time, and you switch it off. Then you wait 7.5 seconds and turn it on again. You just keep flicking that switch over and over, each time waiting for half the previous interval, faster and faster and faster.
Now, just like with Achilles and the tortoise, this is another one of those convergent series. 30 seconds plus 15 plus 7.5 and so on, that infinite number of time intervals adds up to exactly 1 minute. So at the 60-second mark, your infinite task of flicking the switch is totally complete.
And that leads us to the final, really unsettling question. After an infinite number of switches have been completed, at that precise 1 minute mark, is the lamp on or is it off? Think about it. For any on state, there's always a later off state. And for any off state, there's a later on. The sequence doesn't have a final action. So what's the answer? Maybe some paradoxes aren't meant to be solved at all, but are just there to show us the absolute limits of our own logic.